Hi, welcome. Welcome. In this video, we'll talk about multi-channel ADC, or in other words, here's my ARM Cortex M7, and the goal here is the following. We have two different ADC channels that we'll set up. We'll grab analog signals separately from on into these channels, but in order in order to make sure that both of them are being sampled at the right rate, we'll add a timer and use that timer to use a sampling rate of 8 kilohertz for this example and bring those analog signals in through those two ADC, separate ADC modules, ADC One and ADC Two. So let's get started. So before we get started, let's make sure we look up the Nucleo 144 board. That's what we'll be using. The Nucleo 144 user manual says that the A0 connector on the CN9, A0 connector in the CN9 and the A1 connector on CN9 as well belong to ADC 1, 2, or 3, channel 3, and ADC 1, 2, 3, channel 10. We will configure A0 with ADC 1 and we'll configure channel A1 right here with ADC 2. So that's what we'll do. So let's get started with CubeMX. All right, so I've started a CubeMX project here for the STM32F746 Nucleo 144 board. I cleared the pinouts. I've done the project settings so that we write code to using MDK-ARM, so it'll generate code for MDK-ARM. And the default settings that we have had in the past where we create peripheral initialization as separate .c.h file and we'll copy only the necessary libraries. That's what we're going to do. So today, first, let's set up the ADC 1 and ADC 2 channels. Now we saw earlier right here that ADC 1 and ADC 2 were on A0 in 1 and in 3. So ADC 1 in 3 ADC 1 in 3 will be mapped to channel A0 on the Nucleo board. And we'll do similarly ADC 2 channel 10, which will be then mapped. ADC 2 channel 10 will be mapped to A1 on the CN9 connector of the Nucleo board. We have that set up, so that's great. Let's set up the system so that we can do serial wire debugging. So that's all set up. The final thing we'll set up is we'll choose a timer, and for this case we'll just do timer 6. It's a simple form of timer. All we have to do in this case is set as to be activated. So let's go to clock configuration where we will set the default clock to be 216 megahertz. When you do that, it'll ask me, all right, so it's been set to 216 megahertz. Oops. My CubeMX window just went away. Here you go. So 216 megahertz. Now, when you set that clock, you see that different peripherals will get different clock frequencies. So we need to find out whether our timer 6 is on which APB bus. Either it's in the APB1 bus or the APB2 bus, because if timer 6 is in the APB1 timer box bus, then we'll initially be giving the timer a frequency of 108 megahertz. If it is in the APB2 bus, then it'll be getting a frequency of 216. And since we want a sampling rate of 8 kilohertz, it's first important to find out which channel timer 6 really sits on. So let's go do that. And to do that, so from 216, we will find out next which channel it sits on. So if I pull up the STM32F7 reference manual, the STM32F7, not the Nucleo manual, but actually the reference manual. On the first table on that manual, it has a memory mapping, and it shows that the timer 6 memory map is at this particular location, and it is actually placed in the APB1 bus. That means timer 6 initially is getting the APB1 timer clock of 108 megahertz. That's where we'll start from. So here we have 108 megahertz 108 megahertz for the APB1 bus. So we'll go configure timer 6 in just a second there. Under configuration, first let's set up the ADC1 configuration. ADC1 configuration, we can leave everything at default. There's only one channel we're getting. We'll do it through software, so that's okay. Same thing with ADC2. We don't have to change any of the configuration. However, in timer 6, now let's go here. what we want to do is we want the timer to start counting from 0 to some number that will give us the 8 kilohertz frequency. We'll find out what that is. And when we get to that count, what we want to do is raise an update flag. So that's what we've done right here. And when that update flag is raised, we want to enable its interrupt. So I set up the NBIC settings for timer 6 to be enabled. So I'll say OK for now. But we still haven't configured right now it's counting only up to 0. That's the counter period or the auto reload register. That's what it's called. We need to set this value to a proper value that give us the 8 kilohertz frequency. So let's go do that first. So in order to do that, let's go and look at our timer 6, what timer 6 looks like in terms of the hardware. So here's my hardware for timer 6. So initially, this is basically the default architecture for pretty much all the timers that are in the Cortex M7. So we get the bus clock. In this case, since timer 6 is in the APB1 bus, whatever bus clock we're getting from on the clock configuration settings, in our case 108 megahertz. That goes through. That can be downscaled by putting a value in a pre-scale register. In our case, we'll leave that by default to 0 so that we don't change the bus clock. So bus clock was 108. We'll set this to be 108 as well. And that clock basically drives the counter for the timer 6 module. So that counter will count from 0 to 2 to the power 16 minus 1, which is 65536 or 65535, a total of 65,536 counts. However, doing that will be really, really slow. So what we want to do is we want to set the counter to count only from 0 to a particular value, and that particular value is set into the ARR register. By counting only up to the value of the ARR register, we'll actually be setting the clock frequency to whatever it is that we desire. So let's do that. So here's the clock we just talked about, the prescaler, and we want to be generating an interrupt every 8 kilohertz. So in order to do that, we'll take the clock frequency here, and that divide by whatever value we store in there gives us the interrupt frequency. In our case, the clock frequency is given by 108 megahertz. That's what we have. This is the interrupt frequency we want. That's the 8 kilohertz. And we need to figure out what we are adding into what value we're storing in there. So if we do this calculation, we will come up with a value of 13,499 in the case of the ARR register. So let's go put that in the QMX setting. So timer 6, what we want in the ARR register is 13,499. Say apply and say OK. We'll generate the code from here. So we'll generate the code. All the other settings are good. So let's generate the code. And that brings us to the reload. Yes. I had opened up QMX before. So here it is. It's loaded the new code now. All right. So great. All right. What do we need to do here? First of all, what we want to do is let's declare a couple of private variables. I'll call them uint32. So we'll declare a 32-bit unsigned integer, 32 underscore t. I'll call it ADC underscore data 1. In this case, we'll just collect 1,000 points, let's say. And let me just put a comment so that I forget. ADC 1 channel 3 data here. We'll put a square wave to this. All right. uint32 underscore t. I'll call another memory to store the channel ADC 2 channel 10 data here, and let's add a sine wave. I'll set up the function generator to add a sine wave there, and that's just for me to remember why I did that. I just want to create a uint32 underscore ti equals 0. This will be my index into the memory. So index for my memory ADC memory arrays. All right, great. We've just created ADC memory arrays, so let me save that. Great. Now, We enable timer 6 interrupt. So if I look at, so by default, we open to this view with the source files. Let's go to the functions. Under functions, if I look at the STM32F7XX_IT, that is the file that has the function handler, interrupt handler functions. So let's go dig in. Let me also compile this in the process. So by default, the function timer 6 global interrupt will call this interrupt handler. So every 8 kilohertz, once we enable the timer, so let's actually go do that. Let's enable the timer in the main function. And every time we enable the function, the timer 8 kilohertz rate, or 1/8000th of a second, we will get into this interrupt handler. So in main, we'll go and first, after initialization of all the peripherals, right here inside user code begin 2 and user code end 2, what we will do is we will add HAL timer. Let me see. I can't remember the name of the function, so I'll go look it up on my timer.c. And on timer.c, as I scroll through my function, I see HAL time base start with a interrupt. So HAL time underscore base start, and I'm using timer 6, and we're doing this with the interrupt, so that's my main. All right. Oh, compilation is still going on, so let me save in just a second. So I've started the time base. Now, 1/8000th of a second later, I get into an interrupt, which takes me to this interrupt handler routine. From that interrupt handler routine, notice that it calls a HAL time IRQ handler with the timer 6. All right, so if we right click on this, and once the compilation is done, if you right click and say go to definition, it'll take us exactly to that. So that's a timer interrupt handler routine for all the timers that are available here. Now timers are complicated. Some of the timers can do capture compare, input capture, all that kind of stuff. So we are primarily interested in the timer update event. So every time our timer goes from 0 to the value we assigned in the ARR register, that was 13,499, we'll get a timer update flag. And when that timer update flag gets raised, we get to this function. And when the flag is high, so it's not equal to 0, we get to this function and we'll execute this. So HAL time period elapsed callback function. So let's go find out what that function does. So if I right click and say go to definition of that, I see that it's a weak function. So this is the function we should implement in our main routine. This is the function. We'll create the stronger version of that function so that we do what we desire once that update is created. So I'll put this under user code begin 0 and end 0 in our main routine. And inside this, what we'll do later on is we'll add our code. So this is a part of the interrupt service routine for timer 6. And in that interrupt routine, what we want to do is we want to start the ADCs, both ADC 1, and we want to do the same thing for ADC 2. Okay, we've started the ADCs. Next, we're going to poll for conversion. HAL ADC poll for conversion. We'll do its ADC 1, and let's just wait 1 millisecond. We'll do ADC data 1 is the memory in which we'll store the value from the first ADC channel. ADC data 1I equals HAL underscore ADC get value. So this will read from the data register of the ADC1 unit. And we'll do the same thing again for ADC 2. So remember in ADC 1 we had enabled channel 3, in ADC 2 we had enabled channel 10, and we'll do the same thing here, except we'll store it in a separate memory. And once we're all done with that, what we'll do is we'll do HAL ADC stop 1, and we'll do the same thing for HAL ADC stop 2. we'll increment our memory index. And if we've captured at least 1,000 data points, in our case, we'll basically say, stop the timer interrupt. We don't want to collect any more data. That's what we're saying. So once the timer interrupt stops, we won't ever get to this routine, and we'll not be collecting data from the ADC. So our goal is to capture the first 1,000 data points for each of these channels right here. So that's what we've done. So we've started, we pulled for conversion and grabbed the value from HAL ADC One. This is ADC Two. So we grab the data and put it into ADC underscore data registers, 1 and 2 that we've created. Now, this should all set. So let's see. In the main routine, we have started the timer, which will take us to a interrupt service routine. That's in the it.c. That in turn calls the interrupt service routine that is in the STM32F7 time.c. Remember, this file is generated from CubeMX. In that, we get to the interrupt service routine, which then checks how did we get there. And in our case, we got there through an update. So it takes us to this weak function that's pretty fine. We basically create a stronger version of that function in our main code, and we'll execute the ADC reading and so forth. So let me save this and compile this. And once it's compiled, I have a circuit set up where a waveform, let me see, the waveforms are set up in this fashion right here. So I have a function generator set up where the first channel, or ADC1 channel, is getting a square wave, 1 kilohertz, 0 to 3 volt peak to peak. And the second one is getting, let's change this to a 2 kilohertz or waveform, a sine wave that goes from 0 to 2 volts instead of 0 to 3 volts. Okay, and we'll try, let's see here. So I think we're all set here. The function generator is now running. So one of them is a 1 kilohertz waveform, the other is a 2 kilohertz waveform, and we'll try to capture that in our debugger. So let me hit the debug window. This will download code into the Nucleo board. So the Nucleo board has now been flashed. And in the debugger, I am going to watch a couple of variables. So let me move this out of the way. So I'm going to watch the ADC1 and the ADC2 variables. So I've set that up right here, ADC1 and ADC2 to be watched. And what I'm going to do is I'm going to basically hit run. Okay, so you saw that the data just got populated. Let me stop this first. Now let me just do a quick check to make sure that I intuitively can understand whether I'm getting the right sampling rate or not. So for example, ADC1 was getting the square wave, 1 kilohertz square wave, 1 kilohertz square wave. I'm sampling this square wave with an 8 kilohertz timer base. So that means I should get a total of 8 points that make up a complete square wave. So 4 for the high. So since I've started here, so I should get 1, 2, 3, 4 points on the high side and 4 points on the low side. And the pattern should repeat. So let's go check here. So ADC data 1 was storing this. So I have 1, 2, 3, 4. So these are 12-bit ADC. So 4 highs, 1, 2, 3, 4 lows. 1, 2, 3, 4 highs and 4 lows. So that looks like I'm getting the right sampling of my signals. And once in a while you see that the number jumps instead of 0, there's a 17 because there's a little bit of noise when you sample things. ADC2 is sampling a square sine wave. It's harder to tell just by scrolling through the data point like this. So next, what we'll do is we'll grab these values and make sure that we're actually, in fact, getting a square wave and a sine wave. So in order to do that, let me stop the debugger is stopped. So under debug, I can do a function editor. I have a function edit function that I showed you last time, or we've used this previously. So I'm basically going to log my 2 ADC channel like this. I have a for loop set up. Instead of 1,000 points, I'm just going to capture 100 so that we can actually see the waveforms better. Because with 1,000, we're going to get too many of the full waveforms. So let's just do 100 for now. Okay, so we'll grab these two. I'll say save, compile, and here I'm going to type save vals, uh, this. Okay, great. Now I am going to open that particular file on the log. So here's my file that has been opened. Uh, let's go paste this in Excel. So I'm going to bring up an Excel file. I've set up two. I'm going to put these two channels here, and I already set up a waveform window so that as soon as I paste it, hopefully the graph should come up here. So right here. So what do I see? So let me change this page layout or charts layout so that we can see this. All right. Here, so I have 8 kilohertz, 1 kilohertz square wave, and a 8 kilohertz sine wave, 2 kilohertz sine wave sample with 8 kilohertz frequency. So I got the square wave, here's my sine wave. If I sample with a much higher frequency, I'll get a much cleaner looking sine wave. Okay, so that basically concludes this video on how to use two separate ADCs, both sampled at a regular rate. We use polling in our case. We could use DMA and off-source that to the DMA, or we could use ADC interrupt and all that kind of stuff. But the idea was we wanted to sample two separate channels with a help of a timer that's set to a predefined sampling frequency.